1964, a physicist named John Bell wrote an equation. It did not describe particles. It did not describe forces. It described limits. Limits on how reality itself could behave. For decades before that, quantum mechanics had disturbed physicists. Particles seemed connected in ways that defied intuition. Two particles could interact, separate, and still behave as if linked, no matter how far apart they traveled. Einstein hated this. He believed in locality, the principle that objects are only influenced by their immediate surroundings. Nothing should affect something else instantly across space. No influence should travel faster than light. He called quantum entanglement spooky action at a distance. He assumed it meant quantum mechanics was incomplete. Bell asked a different question. What if we test it? He derived what is now called Bell's inequality. It was not an interpretation. It was a measurable boundary. If reality were local, meaning influenced only by nearby events, then certain statistical correlations could never exceed a specific value. If experiments violated that limit, locality would be false. This was not philosophy. It was In 1982, Alain Aspect and his team performed one of the first decisive tests. They created pairs of entangled photons and sent them in opposite directions. They measured properties such as polarization under rapidly changing detector settings. The results were clear. Bell's inequality was violated. Reality exceeded the limit that locality demands. Later experiments became even more precise. Loopholes were closed. Detectors improved. Distances increased. In 2015, experiments in the Netherlands, Austria, and the United States closed major experimental loopholes simultaneously. The conclusion held. The universe does not obey local realism. At least one of two assumptions must be false. Objects have definite properties before measurement. Nothing influences something else faster than light. Quantum experiments show that we cannot keep both. This is not speculative. It is measured. When two particles are entangled, their measurement outcomes are correlated in ways that cannot be explained by local hidden variables. The correlations exceed what classical probability allows. And yet, no usable signal travels faster than light. Relativity is preserved. So what is happening? The mathematics of quantum mechanics predicts the correlations perfectly, but the interpretation remains unsettled. Some say reality is not local. Some say properties do not exist until measured. Some say many worlds branch. Some say hidden variables are contextual. But the experiment remains. Reality violates intuitive separability. The particles, once connected, do not behave independently. This does not mean messages travel instantly. It means the state of the system cannot be decomposed into separate local pieces. Reality is not built from isolated objects. It is built from relationships. And this is where the tension becomes psychological. We perceive space as separation. Objects here should not depend on objects there. Distance should isolate. Quantum mechanics says otherwise. At fundamental levels, separateness may not be absolute. Entanglement has now been demonstrated over hundreds of kilometers. Even satellite experiments have confirmed entanglement between Earth and space. The deeper we test it, the stronger it holds. Non-local correlations are not rare anomalies. They are foundational. Quantum technologies now rely on this. Quantum encryption uses entanglement to guarantee security. Quantum computing exploits superposition and correlation. This is not fringe physics, it is operational. But emotionally, the implication remains difficult. The world appears local because decoherence hides quantum behavior at large scales. Interaction with the environment destroys fragile correlations. Classical separability emerges statistically. But beneath classical stability lies quantum connectivity. Reality is layered. At our scale, objects appear independent. At fundamental scales, systems are relational. Bell's experiment did not prove faster than light communication. It proved that classical locality is not the full story. Einstein was wrong, but not carelessly. He was defending consistency. Quantum mechanics preserved consistency differently. Instead of locality, it preserved mathematical coherence. The lesson is subtle but profound. The universe is not stitched together from independent pieces. It is structured by constraints that operate beyond intuitive separability. This does not make the world chaotic. It makes it relational. And that relational structure is measurable. When physicists say quantum mechanics is strange, this is what they mean. Not that it is vague or mystical, but that its predictions violate classical expectations about independence. Bell's theorem is one of the rare moments in science where philosophy became experiment. An experiment answered. Local realism cannot describe reality completely. This does not mean we fully understand what replaces it, but it means something deep about the universe has been revealed. Separation may be emergent, not fundamental. Still, within